So when we talk about smart cities, and then we start to think about research that goes into smart cities, it's important to remove the complexity layers and really boil it down to fundamental questions that from a research perspective we can answer. So when we look at smart and connected systems, I like to always think in terms of three main questions that we want to look at from a research perspective. Where, right? So when we think about where, it means where is this system being deployed? Again, if you have a communication system or a sensing system that is deployed on the human body to monitor vital signs, the way you structure it, the way you design it, and the way the nodes will communicate is completely different from if you deploy it on a bridge, for example, for structural health monitoring, or if you deploy it on a plane to monitor the health of the plane itself, or if you deploy it in agriculture to make sure that you're doing agriculture the right way. So the context under which you deploy a network heavily impacts the network performance. The next thing is how do you build it, right? How can we build communication nodes that are spectrally efficient, that are aware of their resources and aware of the network resources, and at the same time are being designed to be ultra low power? And then the final question is what, right? So what do you do with all this data? Now, the problem is that as you start to build all these smart sensors, you're going to get a huge amount of information. How would you handle all this information, and how would you be able to process it in a seamless way and a timeless way is another question that you would need to think about. So where, how, and what are fundamental questions that you would always look for when you address research in a certain topic. Along these lines, I'm going to take two examples of research that we do in our work. The first one is research that actually concludes this year. It's been a 4-year-long project between us and the University of Michigan in Ann Arbor. And essentially, it looks at being able to use sensor networks, especially in big cities, to figure out the structural damage that happens to a city after an event. What do we mean by an event? An earthquake, for example. If an earthquake strikes a city, then the city is going to be unsafe for the residents for some time. What you want to do is that you want to be able to tag it very quickly, saying a building is unsafe, so we need to either evacuate or fix it, or a building is safe. Now, believe it or not, in this day and age, in 2021, people still have to physically go to a building, by people I mean engineers, and test the building to see whether it's unsafe or safe, and then give it a tag. But in the fact that we have all these sensors should not make this the case. We should be able to do this in an automated way. But then there's, of course, the concept of cost. It becomes very expensive to do that on every building in every city. Hence, we thought about using what we call citizen-owned electronics, whether it's game sensors or tablets or phones or you name it. Each one of us has multiple sensors right in your hand. For example, in my case, I have my cell phone placed right on my table next to me in my office. That cell phone has an accelerometer in it, and accelerometer can measure acceleration. Hence, it can measure the impact of an earthquake. So the idea that we had at a very low level is if an earthquake happens and I have a number of smart devices inside a building, then I can use the readings of these smart devices to be able to detect the impact of the earthquake on a building. Then I can transmit that to the authorities, whether it's police, firefighters, EMR. But in the interim between transmitting it and getting them to respond, I have to make sure that I can process them in a certain way, and we'll talk about that later in this talk, so that I'm able to make the signal good enough so that it gives good enough information. So the main question that we need to look at is, what does good enough mean? And how can I do that using either local processing or cloud processing? And then we can send that through a disaster map to the authorities so that they can respond. Very briefly, without going into a lot of math, when you have a shaking for a building, the floors would move in different modes. You can think about it as a sine wave propagating through the building. By measuring the difference between the ceiling and the floor, which we call the inter-drift ratio, the IDR, it's a very good indicator of the health of the building by seeing what is the peak deviation that happens. So what we want to do is that we want to have a sensor on one floor, a sensor on another floor, and we want to compute the difference between these two sensors so that we can measure the displacement. The next question you're going to ask me is, well, how accurate should it be? It should be in the order of centimeters. So we want it to be very accurate in order to be able to measure the health of this building. And then based on that IDR, we can say whether it's okay to get into the building. the building has issues or is going to collapse. Okay, so the first challenges that we had is we have a cell phone. The cell phone is placed on a table. What kind of noise affects the cell phone, and how can I improve the reading of a cell phone? So there's a lot of work that we did in terms of reading the accelerometer, figuring out how to filter it, figuring out the different types of noise that impact it, whether it's angle random walk, bias instability, or rate random walk, and being able to mathematically model this noise. Then after that, figuring out how to correct for it on a local level. So each cell phone would take this reading and correct it, and then give us a displacement estimation. Now, just so that you know, and reminding you of some undergrad work you did, we can go from acceleration to displacement by performing double integration, right? So we integrate from acceleration to velocity, and then from velocity to displacement. Now, if you do double integration, whenever you integrate something, you know that you're going to get a lot of noise. So we used an interesting thing to look at, which is the fact that whenever something shakes, right, it goes from one side back again, there's a point of zero velocity where it stops and then reverses direction. So when it stops and reverses direction, that's a piece of information that you know that it stopped. We call this a zero velocity point. So we use this zero velocity point, which is we call ZUPT, zero velocity update, in order to correct the readings that a local phone would do. And this is used in many different techniques for pedometers and so on. Then we did some interesting mathematics to be able to create a correction term that corrects the error that we get out of a specific cell phone so that we can improve the readings of that specific cell phone. And for those of you who are interested, we have many papers in that I'd be happy to share. Now, the results of ZUPT were interesting. So on the x-axis here, we have the integration time. On the y-axis, we have the displacement. Remember, we're trying to get this displacement in the centimeter range. If you don't do any correction, you can see that as you increase time, the integration error starts to grow out of hand, and really the cell phone reading becomes useless. With this ZUPT approach that I just described, you'll be able to take this noise all the way down to below 10 centimeters. So this is encouraging, this is good, but this is not good enough. You still have 10 centimeters variance, right? And that's not good, standard deviation. So this is where another technique is done, which is crowdsourcing. It's not only one cell phone that you have in a building, you have many cell phones. So if I'm able to collect readings from multiple phones, right, and take all these readings and send it to a cloud server, then at the cloud server, I know that there is a common excitation, which is the earthquake, and all these devices are responding to a common input. Because they're all responding to a common input, then I can use that information to clean the signal, and I can get a really good signal out of these multiple readings. So this crowdsourcing really improves the performance and makes you able to use these sensor networks into a truly massive sensing station. So let's look at readings, right? This I'll go very briefly over some experiments that we did. So we got a cell phone, we put it on a track, so it can go up and down this track. We used a laser camera that can take a picture of the cell phone as it moves. And we use two techniques to measure the displacement. One technique is the laser, which is very accurate. And another technique is the accelerometer inside the phone itself. Now, we use that simple phone. It's a Galaxy S7. As you can see from this specific curve, which on the x-axis has time and on the y-axis has velocity, you'll find that the OptoTrack, which is the blue laser-enabled tracking, gives a certain reading, while the accelerometer gives a much more offset reading. So there's a lot of error, and that error increases with time. Now, if we take ZUPT and use that approach of knowing that there are zero velocity points that we know exactly where that happen, we can improve the noise quite dramatically, right? So we can get quite a good reading where the cell phone and the laser system give very similar readings. Not only that, but if we combine multiple readings from multiple phones over time, in this case, for example, 1 phone, 2 phones, 3 phones, up to 9 phones, you can see that the error starts to reduce for different earthquakes. We tested 3 different standard earthquakes. Whether you look at the error, absolute error, or the root mean square of the error, you can see that it's always decreasing. So that's good news. So basically, we found that we can get a really good performance, not just from the cell phone by itself, but from the cell phone and the combination of multiple cell phones. our colleagues at Michigan built a small building. It's a small mock building. It's a model, which means it's a smaller scale than the main building. And we used a 4-story building to highlight the impacts that we can see on multiple floors, whether it's on the first floor, second floor, third floor, and fourth floor. And you can see that the IDR now is within less than 10% as we had initially wanted. So the intention of this discussion on sensor networks was to show that using sensor networks leads to sustainable and resilient communities. In what sense? In this specific example, we can see that we can increase the speed and accuracy with which building damage may be assessed. It allows the first responders to optimize their response and be able to really send their resources on where it's needed at the right time. It enables, and most importantly, it enables seamless and rapid instrumentations. There is no cost associated because the citizens who live in areas that have earthquakes, whether it's Japan, the US, or any area that is subject to natural disasters, have a vested interest in enabling this kind of sensing. So they would want to install these apps on their cell phones, and therefore the cost to deploy a city-wide sensor network is almost zero, right? So you just develop the app and people will download it. Finally, you create a nationwide database because every time an event happens, you record the response of the building to that event. So over time, you'd be able to know which buildings are good, which buildings are bad, and also to be able to develop nationwide responses and nationwide golden codes on best practices of how to build buildings. So that's really an example of where we took a sensor network, we took a local processing, cloud processing, and we showed how all this could come together. So going back to smart and connected systems, we discussed a little bit about where. We discussed the fact that in this case, we had a citywide sensor network. We discussed how local processing on a specific cell phone could improve the signal of that cell phone. And then how we can use communication to go up into the cloud, where the cloud would do the merging of all the readings that it had. And then you would send it back to a government agency in order to respond, in this case, the first responders. Now I'm going to take another extreme example, which is body area networks. In body area networks, that is a very different kind of setting, because in body area networks, all the nodes are deployed on a body, right? And these could be used to monitor fitness, they could be used to monitor health, they could be used for preventative health, and so forth. But in the end, you also want to be able to collect the information from your body and use that to provide you with information that you would act on, whether it's for your health, again, as I mentioned, for preventative medicine, or for actual diagnosis. So that has a completely different set of requirements and would lead to a completely different design. So we'll talk a little bit about that kind of sensor network. So as I mentioned, what you would love to do is that, for example, we have this very fit person who's running and he wants to measure his performance. He has these sensors put on different aspects on the chest, on the feet, on the hands, and they're providing him with information about his performance. The issue is, right now, all these devices are available in the market, but they're all wireless in the sense that they all use RF technologies, whether it's Bluetooth, Zigbee, some sort of wireless technology, and all of them require to be powered by a large battery. They require the use of an antenna, and therefore it's not a seamless experience. It's an experience that is expensive on a per node basis. It's an experience that requires that you have all these different RF emitting systems put on your body, which may or may not be healthy, and there's a lot of discussion about that. And to date, it has not picked up. Now, what we're thinking of doing is, well, all these sensors are actually placed on the body, and the body itself is conductive. There is no reason for them to go on an antenna, hence all these cancellations of the antennas. In other words, we do not want them to communicate off the body because they're already on the body. So they should be able to communicate using the body as a channel, and therefore getting rid of the analog front end, getting rid of the antennas, and using extremely low power communication so that they can communicate together through the body. And then eventually one of them would connect to your cell phone, which would become the gateway to the outside world. So you can see that this is a very different design of a network mandated by the deployment of the network itself, in this case, the sensor network. Another thing that we want to achieve by doing that is that you get a 10x power reduction. So why is that the case? Because all the other wireless technologies, whether it's Zigbee, Bluetooth, IEEE, different versions of Wi-Fi, and USB, they all have, as I mentioned before, the analog front end, and they have the antennas. Versus the body area networks require a relatively low bit rate, right? So you're monitoring the heart rate, you're monitoring vital signs, you're monitoring different aspects that require very low bit rates. So you don't really want to be sending at a high bit rate, unless, of course, you have a video, for example, surveillance that you're sending. But most of the cases, you're operating here at a low bit rate. And at the same time, we want to push the envelope in power consumption to be at least 10x lower, so that you're not creating any issues in terms of tissue heating, or you're also extending the battery life. So the first set of research that we did was to identify, well, what is the best data carrier that can take information of two nodes placed on the human body and communicate between them? What are the options? The options are, of course, electromagnetic waves, or magnetic fields through magnetic coupling, or ultrasonic waves. So there was some research that was done in many different groups, including ours, on identifying which one of these would perform the best. And the consensus now is that electromagnetic waves would perform the best, especially because they decouple, they're decoupled from an antenna size. In other words, at this level of radiation, they do not need an antenna, and therefore they would basically connect directly through the human body, as if the human body is a circuit, essentially. So that was the first set of work that we did. Now, if we assume that we have a transmitter with electrodes, and then the body itself being the channel, and then electrodes, and then the receiver, how can we come up with a circuit model that captures that? So that was the next set of work that we did, which is identifying how the equivalent circuit model, if you will, of communication between the transmitter node and the receiver node could be modeled using circuits. Again, this is work that has been done in many different groups, including ours, and they all looked at how different tissues, whether it's skin, fat, muscle, bone, bone marrow, all of these impact the electrical characteristics of the human body. And then eventually, any goal of any communication system is to come up with a channel model. Once you have a channel model and you understand the channel that exists between the transmitter and the receiver, then you'll be able to create a system that can take advantage of the knowledge of the channel to enable the most efficient communication between the transmitter and the receiver. Now, this channel model is, of course, highly dependent on who the person is, whether it's the female or male, whether they have a small frame, a medium frame, a large frame, and so forth. And therefore, like wireless, you'll end up creating a channel that is statistical in nature. In other words, it is a parametric channel that you define the parameters, and you would get a statistical model that represents that specific channel. So in order to do these tests, again, this is a multi-year project. It's not something that we just started. We've been working on this for many years. So we started first by looking at electrodes. How can the electrodes be designed? What kind of electrodes do we have? And then we started to look at, now that we understand the characteristics of the channel, how can I test the channel? One way to test it is through simulation using finite element modeling. And finite element modeling, for those of you who don't know, is basically dividing any surface into smaller grids and then solving the electromagnetic equations on these grids. And this is a very accurate method of simulation, but it's extremely time-consuming. So that's one way that we can simulate things. Another way that we can emulate things is to build phantoms. So what are phantoms? Instead of testing on human beings, we create tissues, or we create structures that have the same electrical characteristics as tissue, as human tissue, in terms of conductivity and permittivity, and therefore we can test on these phantoms exactly the same way that we would test on a human body. So the first thing we started was creating these models in the simulator, in HFSS, which is a finite element method simulation. And we wanted to see, as we start to test whether skin or fat or muscle or all these different combinations, how do electromagnetic waves really transfer between the different nodes? And we created a model, a channel model. That was the first step. The second step, we started also to study, what if there are certain internal metallic structures? Like many people who have certain breakage of bones would end up having these plates, metal plates inserted in the bone. Now, when you start to insert metal plates, that also creates a big variance in how electromagnetic waves will propagate. So we also studied the impact of that on the overall propagation of electromagnetic waves between a transmitter and the receiver. In the end, we created a complete model. Then we started to compare our model versus the model that we created by simulation. In this case, the RED model by simulation using HFSS, and the circuit model, which we created using our own circuits, and we compare the two together. And in the end, we can see that there is a very close match between the two obtained circuit models, whether it's the long simulation HFSS or the circuit model across different frequencies. So that was the first set of work that we did in the area, which is creating a channel model that reflects really the different channels between a transmitter and the receiver placed on a channel. In this case, the channel is the human body. The next set of experiments that we did were phantom-based, which is, can we create a material that has the same characteristics as the human body so that we can test on it various configurations? And in this case, we also were able to successfully do that. And we could mimic different combinations of, again, different combinations of tissues so that we can test it. Then finally, we were able to test it on human subjects and compare the channel for the different human subjects and for the different phantoms that we used. As you can see, the channel has certain, like a wireless channel, it has certain areas that are frequency selective. So some frequencies have major dips, other frequencies go down, then it goes up again, and then there are other frequencies that are different. It differs from one person to another and from one measurement condition to another. Hence the need for us to be able to create this statistical channel that we can use to characterize the communication between different nodes on a human body. Now, once we've got beyond that, once you have an accurate channel model and you really understand how to characterize the channel, what can you do? What are the use cases that you would be able to use this in? So let's take examples, right? In this case, we're looking again at this concept of sustainability. How can we build a sustainable healthcare system? Imagine you're sitting at home, some person has some chronic condition. That chronic condition might require monitoring their kidneys, monitoring glucose, monitoring their brain activity, monitoring anything that is specifically linked to a long-term disease. Right now, the way that it's being done is that you either have very invasive wires that are always connected to your body, or you take snapshots by going to a doctor every once in a while for the doctor to be able to take measurements. What we could do in this case is, if we have this continuous measurement, then that would be sent through a secure personal cloud to a doctor, and the doctor or the healthcare practitioner would be able to constantly monitor your activity, of course, with your own permission. If you don't want that to be monitored, you would stop that. So that's one way. Self-care, fitness. If you're into fitness and you want to make sure that you are measuring, you are performing at the best level that you can, right now people use smartwatch, but you can always extend that so that you can monitor your muscles, you can monitor your performance over time. And right now, it's simply not possible because it's not a seamless experience. It's very expensive. It requires a lot of RF units that you don't want to go there. And then finally, monitoring of people who have very difficult jobs, whether it's firefighters, whether it's pilots, whether it's any kind of a job that really requires you to be at the peak of your physical performance and requires your colleagues to know that you are fine. So that would also be another example of where you would deploy these sensors. So all these are use cases. Now, another use case that was very interesting to us and also was very interesting to a company, basically Bloomberg, is the security applications of this specific technology. In other words, can I use the human channel to say that this person is who he is, right? This is a great example of industry academia research, because Bloomberg is a financial company that is a very large financial company in the US. Got very interested in this work, and in fact, they had a joint patent with us on the applications of human channel identification towards security. In other words, can you put a patch on your hand, and anytime you touch something, whether it's a keyboard or a door or something within a secure area, it would immediately identify that the channel between the patch on your hand and the subject or the item that you touched is indeed your own human channel. And why is it unique for different people? Because every person has a different composition, whether it's how you look, whether it's the tissues that form your hand, for example, they are unique to a specific person. So what we did is that we wanted to really quantify that. So we did some tests using a vector network analyzer, and that involves basically identifying the signal transmitting a signal through the hand, for example, observing the channel gain and attenuation profile, extracting unique features, and using machine learning to train for biometric identifiers. So the machine learning techniques will basically help us identify that this is indeed you. Okay. So what kind of features did we extract? We used the gain for certain TX-RX separations. We used the gain for all separations. We used the power bins in frequency to be able to identify the frequency response of the channel. And then we used machine learning techniques to identify the accuracy, precision, recall, and what we call F-measure for those of you who are working in machine learning. So how accurate is this? It turned out to be actually pretty accurate. So depending on the different technique that you'd use for machine learning, you could get up to 98 or 97% of accuracy. And again, that's for a simple experiment that we did where we want to differentiate one user out of 10 users that are known to the system. So that's called identification, right? So you have 10 users or 10 people who have access to a certain area, and we want to figure out which one of the 10 is the person who tried to access an area. So that's called identification. An even more difficult problem is authentication, which is if I have one person who's trying to access an area, and there are hundreds of other people that I don't know their channels who are trying to access that area. Can I really say that this is the person that I want out of these hundreds of thousands of signatures? So authentication is always a much more difficult problem than identification. So for authentication, in order for us to train the machine learning approach, we had to use a little bit of a smart approach. We created users. So we used statistical models to generate distorted signals that are outliers for training the authentication model. In other words, we said, here is one model, and then we created all the possible combinations of other profiles, if you will, that could access or try to access this specific model. And then we trained the machine learning model in order to be able to create authentication. And in this case, we tested it directly on subjects, and we achieved pretty good accuracy as well. Not as good as identification, so it's now 96% versus 99 and 98% in the previous, but nonetheless, 96% for this challenging test turned out to be pretty good. So this takes us back to the original questions that we were looking at, which is how can sensors and sensor networks address fundamental questions for smart and connected systems? So we looked at two examples. We looked at an example of structural health monitoring, and we discussed what modifications you would need to do for that sensor network in terms of the sensor itself, the local processing, and the global or cloud processing needed. We discussed body area networks and how that is completely unique in terms of what it needs and the different things that need to be done in order to support body area networks. And now I'm going to shift a little bit to how and what, right? So how can you build nodes to be efficient, and what can you do with all this information in the remaining time that we have? So before we talk about how, it's interesting to see what's happening in communication, starting from 1G, 2G, all the way up to 6G. And as the title says, it's what's in a G, essentially is really what happens when you go from 1G to 2G and so forth. So this is a slide that I got from a very nice source, and it kind of gives the major milestones that happened for different generations. So in first generation, it was voice calling. In second generation, SMS. Third generation, the internet kicked in. Fourth generation, there was the Internet of Applications, where you started to have all these applications on your phone. And 5G is basically massive broadband and the Internet of Things. Going on to 6G, this is where you start to get all these applications coming into play, whether it's the use of new spectrum, disruptive technologies, using cell-free networks, disaggregation and virtualization of networks, energy efficiency being a driver, and artificial intelligence. Another way to think about it is that from 1G to 4G, it was a people-to-people connection. 5G focuses on the people-to-thing connection, or the Internet of Things. And 6G will be driven by thing-to-thing connection, including people-to-thing connection. And when you start to think of that, that means that there is a massive explosion in the number of connections that are being done. Now, with this massive explosion in connections, there is also a massive explosion in data. How can you process all the data? what kind of platforms can we develop to process this large pipe of information that we're getting connected to basically our base stations. So this takes us into another direction of the work that we do in my group, which is building specifically computing platforms that are geared towards communication systems, that are geared to handle specific applications of communication systems. In this case, for example, before I go into the details of how this works, it's important to realize that communication systems are mainly vector-driven. In other words, you're always looking at, for example, if we look at different types of modulations, where we have moved into looking at, instead of looking at samples, into collecting samples into long vectors, and then operating on vectors. So when you operate on vectors, there's a lot of energy consumed in taking that vector into memory, doing matrix manipulations, and then taking that back from where it's located back to memory again. So a lot of energy, a lot of computations are wasted in moving information from memory to the computing platform, the ALU, doing the operation and then taking it back to memory. So this has changed over the past few years, where people started to think of, well, why do I need to take it out of the memory in the first place? Why not leave the information inside the memory where it's stored and do the operation on the item or the word as it's stored in the memory itself? In other words, bring the computation to the memory, not bring the memory to the computation. This new approach is called in-memory associative processing, and we've done some work in the area as well in terms of how is that useful in the context of wireless communication systems or communication systems in general, and how efficient is that? So I'm going to skip this animation in the interest of time, and I'll just say that what is the enabler of this approach? So this approach is not new. This approach has actually been around since 1980s in terms of doing an associative processing. What's new is the technology that enables this to be done. So recently, over the past few years, there has been a rise of what we call resistive memories. So resistive memories are memories that are built to become very compact. In other words, we no longer need a large number of transistors. We only need what is called as a memristor. So a memristor is simply the intersection of two lines. So basically, two lines intersecting together create a memory element called a memristor. And you can see it in this diagram here. So that becomes extremely efficient in terms of space, extremely efficient in terms of power utilization or power efficiency. And it allows us to be able to create these very large memories where we can store a lot of information. So that's really the key differentiation that allowed associative processing or in-memory processing to become reality. Same thing for artificial intelligence and machine learning. Machine learning is not new. It's been around for decades. What's new is that there is now technology that enables us to create so many parallel neurons that we can implement them on one platform, and therefore enabling us to do the operation. So, and then it becomes a positive feedback cycle. Because you have the platforms that enable you to do the operation, then you become very creative on the algorithms that you're running or the operations. Then you become more innovative on the platforms, then you become more innovative on the algorithms, and you can see how this feeds the growth of applications such as machine learning or in-memory computing. Now, one of the major applications that any communication system uses is an FFT. So an FFT is a fast Fourier transform, and basically it's one of the fundamental operations used in pretty much all types of modulations that depend on using different, well, I don't want to go into too much technicalities, but it's one of the modulations that is enabling LTE. Right, so LTE is one of the most recent communication standards. Now, there has been a lot of work in terms of FFTs, building efficient FFTs. But if you were able to build it using these emerging technologies of resistive RAMs, then in terms of giga operations per second per watt per millimeter squared, which is basically how efficient in terms of power and area is the architecture, you'll find that using these ReRAMs places it in a class of its own, in terms of the efficiency that it has for processing this very hardware-intensive operation. Now, assuming that we can build this, the problem, of course, will be that it will become very hot. So in terms of watts per millimeter squares, it becomes very hot because it needs to dissipate all this energy. So the intention of this slide is to show you two things. Is to show you that number one, you can build very efficient and very high performance FFT engines, but it's not easy to deploy them because the technology is not there yet, whether it's the cooling technology or the ability to be able to perform all these operations at the same time. Another example that we looked at is in-memory DCT, digital cosine transform, which is again another version of doing an FFT. I'm going to skip this slide. I'll just say where it's applied. One of the major things that people are looking at for artificial intelligence and machine learning is training, right? How can I train the engine? The issue is that it takes a lot of power to train an AI or a machine learning approach. In fact, the MIT Technology Review, I think last year, came out and said, is AI the next big climate change threat? In the sense that, are we designing such a complicated system that it actually is going to impact the climate from the amount of energy that it uses? So even though artificial intelligence or machine learning has achieved great success in performing a lot of complex intelligent tasks, this comes at a cost. And that cost is really how much energy do we invest in training? So we wanted to look at efficient methods that support us to do this training, while at the same time being able to reduce the energy consumed. And this is work that is joined with Professor Khaled Salama and his group. Professor Khaled Salama is, of course, the Associate Dean of the SEMSI division, and also a colleague, full professor colleague at KAUST. So we started to look at how we can implement, using this in-memory computing that I was talking about, how we can implement very efficient architectures for convolutional neural networks. And we proposed different approaches in terms of being able to use the concept of in-memory processing to reduce the energy consumed in training of machine learning approaches. If I may show you the result, I hope it doesn't crash again. Yes. So there is a paper that discusses this in details for those of you interested, but we wanted to show that when you compare it with traditional architectures, whether it's a CPU or a GPU, this approach of associative processing results into much simpler control and much more optimized throughput for processing of these very large vectors. In fact, we showed that we can achieve about a 20% improvement versus the best possible available implementation that is based on a GPU. And it addresses two things. It addresses the computational complexity by using extreme parallel computing. It also addresses the memory access cost completely by doing all the processing inside the memory. So this brings us to the conclusion of the talk, and I'm right on the dot, 50 minutes. What are the research opportunities in these areas that we have in our group? So we have work on machine learning in communication systems and how that can be used to improve channel estimation, improve resource allocations, and so forth. We have a lot of work on sensors for smart cities. We have work on neuromorphic computing platforms, similar to what we just discussed. And we have work on body area networks, similar also to what we discussed in the talk. So with that, we have arrived at the end of my talk, and I would be very happy to entertain any questions you may have.
We do have some question in the Q&A part of the screen here. So the first question is related to LoRa. As you know, Ahmed, LoRa also is another popular kind of IoT type of, let's say, communication protocol. And the question by Ahsan Sajid Khan is, in LoRa-enabled device, most of them ensure long battery life and lower bandwidth. In contrast of LoRa-enabled device, what additional benefits may expect from body area network methods? Is there any scope that body area networks may also work with LoRa? So essentially, maybe a comparison between what we are doing and LoRa, and also how does this body area network kind of interface with LoRa?
So actually, that's a very good question. One of the main things that we're promoting in body area networks versus LoRa, or versus any wireless technique, is you don't need an antenna, right? So the difference is, in a LoRa system, you will eventually have to build a RF section. That RF section will include both the RF processing section, as well as the antenna itself. And as you go to different frequencies, the antenna, of course, can become smaller or larger, but nonetheless, you still need an antenna. So the benefit of body area networks that use the human body itself as a communication medium is that it does not need that. So it becomes very small in terms of area, and also very small in terms of power, because RF in general is an analog system that requires biasing. And anytime you have biased currents, you have a constant drain of current that's running through that section. So I would argue that using body area network would result into smaller, more efficient, and less power consumptions than LoRa.
Thank you, Ahmed. Any other question from the audience? You can check in the chat. That was the only question. I mean, there's a question about the slides. This is something we will kind of, in terms of sharing the slides and so on, this is something we'll see with the speakers. Maybe some of the slides we made available on our masterclass website. We plan to have eventually a YouTube channel, that's my understanding, and some of these talks will be on YouTube. So please keep monitoring our website and our eventually YouTube channel. Hopefully many of these talks will be posted there. Any other question?
So I wanted also to highlight something, is that sensors and sensor networks have many different applications. So this talk focused more on looking at the sensors and sensor networks from an application perspective. There's also sensors and sensor networks from a communication perspective. How would you look at the communication between the IoT nodes and either the front haul or the back haul of the networks? And that's actually one of the main innovations that the speaker from Huawei talked about yesterday, which is how 6G would be able to provide really exceptional interconnection and exceptional bandwidth to be able to treat these different levels of connections, whether it's a thing to core or communication between the machines or communications from humans to machines. So that interconnection and that ability to support a very variable rate of communication is a core requirement of 6G and is something that is being promoted in the new standards. Hopefully that will become into effect by 2030.
Very good point. Thank you.
First thing I did after the talk was to go and buy the book that she had, to be honest. I was very curious about all the work that they're doing at Huawei.
Yeah, thank you. Another, actually, now we don't have any other question, but maybe question similar to the LoRa question. People have been talking now for a few years, I would say, on molecular communication also as a way to communicate within the body. So how do you see this interaction between the wireless body area network that we are talking about and so-called emerging molecular communication type of schemes, which are, of course, at the very early stage, but they are being presented as the future way to communicate within the body?
So that's a very interesting question, Salim. Thank you. So basically, you can think about it in different ways. In molecular communications, you're trying to create different concentrations in the fluids, and the communication happens through the physical change in the fluid. So that's number one. It's a relatively slow approach because you have to wait for the molecules themselves, or the concentrations or the gradient of concentrations to happen. And number two, it requires that you either inject molecules or you change the combination of the fluid in certain ways so that you create, for example, ionizations. And these ions would then migrate from one part of the body to another, or from one end, from the transmitter to the receiver. So these are all, to some extent, a little bit invasive because you don't want to create ionization in the fluids. And also from a speed perspective, it takes a while for a gradient to happen so that it pushes this across a certain range. So for short range communication, it might be possible, but for longer range communication, it might be something that that is difficult to achieve.